Let's talk about the number 12. Now here's how you find the prime factorization. We know that what we want to do is end up figuring out numbers that can be multiplied together to give us 12 because those are going to be the factors. But the only thing that we care about when we talk about prime factorization are the factors that happen to be prime. So an only way to really get at that is to do the following. You start with the number you want and you build what we call a factor tree. So what you want to do here is draw two little branches of a tree. That's why we call it a factor tree. And you need to think about any two numbers you want to multiply together to give you 12. Could be anything. I could put 2 times 6. I could put 3 times 4. I could do anything I want. So let's start and let's say 2 times 6. That equals 12, right? So we've begun our factor tree. Now, this number here is 6. I can further find some numbers that can multiply together to give me 6. So I continue my tree down here and I say this can be also 2 times 3, right? So I'm building a tree and all I'm doing is finding numbers that multiply together, and each branch of the tree I continue doing this. But you see, when I get to a point like 2, yeah, I could sit here and come down here and say that I could say that 2 is equal to 1 times 2, and I could continue the tree, but that's not really going to make it any simpler because the factors, the prime factors that we're interested, are not going to include 0 or 1. So it wouldn't really help me to put a 1 here. That's not going to really get me where I want to go. And 2 is already a prime number. So another way to think about this is I want you to keep building your factor tree. Keep on trying to multiply, multiply, multiply until you finally get down to the point where the numbers at the bottom of the tree, these being the numbers at the bottom of the tree, are already prime. So 2 is a prime number. So we stop. There's no reason to continue. You could continue, but you're going to keep getting duplicate prime numbers, so there's no reason to continue. 2 is a prime number, so we stop. 3 is a prime number, so we stop. So what we have found is these guys here at the bottom of the tree are what we call the prime factor. So if we wanted to write it out, we could say that 12 could be written as 2 times 2 times 3. And think about it. Do it in your head. 2 times 2 is 4. 4 times 3 is 12. And every one of these numbers is a prime number. So these are the factors of 12 that are prime. So this is sort of writing the prime factorization, writing out the prime factors. The factors of the number 12 that are prime is the number 2 and the number 3. And when we ask for the factors, we just list the individual numbers that are the prime factors. But when we talk about writing the factorization, we write it out as a multiplication. And another way a lot of books will ask you to write it is if you have something like 2 times 2, you'll be writing it like 2 squared times 3. You'll use exponents. So these two things would be what we call the prime factorization. And I ran out of room, so that's prime factorization. So when you see prime factorization, you're going to be writing the things out that are multiplied together. This is the same thing as this. Sometimes you might write it in terms of an exponent, sometimes you might not. It depends on what your problem asks you for. But either way is important to know how to do. Now, if we were asked to simply list the prime factors, then we just list the numbers, 2, 3. Those are the prime factors. There's no reason to list 2 a second time because it's a duplicate. So when a problem asks you, list the prime factors, you just go down here to the bottom and you list all the numbers without any duplication. When you're asked to list the prime factorization, then you actually have to write it out as a multiplication and include everything and use exponents if you need to. So, you know, this might not seem clear at first. I mean, I hope that it is, but it might not. What we're going to see as we work a lot of problems is you're going to get good at this, and you're going to see the patterns involved. So basically, factors, don't forget from the previous section, are just finding things that multiply together to give you the number. In fact, 6 is a factor of 12, and there's other numbers that are factors of 12. 4 is a factor of 12 too, but in the end, we don't care about those. When we talk about prime factorization, we keep drilling down this tree all the way to the bottom so that we only care about the bottom of the factor tree, these numbers. And so everything at the bottom of a branch. Now let me show you one more thing while we're here. What if we did this problem again number 12. But let's say we didn't pick 2 times 6 because you're doing your own work. Let's say you pick something else you might commonly pick, 3 times 4. 3 times 4. Totally different set of numbers, but 3 is a factor of 12, 4 is a factor of 12 because they can be multiplied together to give you 12. So what we're going to do is continue going down the tree. I could branch this out, but all I would be doing is 1 times 3. And so I'm not going to do that. 3 is also a prime number already, so there's no reason to continue the factor tree down here. But 4 can be split up into 2 times 2. And 2 is also a prime number, so I stop the tree here. So again, I stop the tree here and I stop the tree here. Next, I'm going to look at the bottom of the tree. This number counts, this number counts, this number counts. And notice the same numbers appear on the bottom in both trees, and that always has to be true. There are different ways that you might end up getting to the bottom by picking different numbers, but in the end of the day, you will always have the same numbers at the bottom of the factor tree if you've done it right, because it's just the way multiplication works. So if I were going to write the prime factorization here, I have the same numbers. It would be 3 times 2 times 2, which is what I have here, 3 times 2 times 2. So the prime factorization is the same thing. The list of the prime factors is the same thing because it's the same numbers and because multiplication works that way. So don't worry about picking the right numbers to start building your tree. That's why they're sort of fun. You can pick whatever you want. Anything multiplied together to give you the number can be used as a starting point. All right, so that is what we're going to learn in this section. That is what we have learned in this section. Now all we're going to do is work some problems. So the first kind of problem I want to work is I want to write a number on the board, and we want to identify if it's prime number or if it's composite number. So it's a simple skill, but it's an important skill. So let's go and do that. All right, let's say, what about the number 19? Is that a prime number or a composite number? What you need to do is think about prime numbers are only divisible by themselves and 1. So if you can find a number other than that can divide into that, then it's not prime. But there is no such number, so this is a prime number. You can't divide this by 7, you can't divide it by 6, you can't divide it by 5. The only thing you can do is divide it by 19 and itself. What about the number 51? At first you might not think of a way to do that, but this is actually a composite number, which just means it's not prime, by the way. So composite is just another word that means it's not prime. The reason is because if you get a calculator out and take 51 and divide it by 3, you're going to get 17. So it divides evenly by a number other than itself and 1. So that's the reason. So you're just looking for something else that can divide into it. What about the number 21? Well, 21 can divide by 7. So this is composite. And that's because 21 can be divided by 7, which would give me 3. Or 21 can be divided by 3. There's lots of different ways to do this. What about the number 23? Is it prime or composite? Well, I'm looking for something to divide into 23, but I can't find one. So I'm going to call it prime. I can only divide this by 1, and I can only divide it by 23. If I try to divide by 11 or 10 or 15 or anything else, I'm not going to get a nice even number. What about the number 41? You start thinking to yourself, or get your calculator out, divide by 10, divide by 7, divide by 6. None of those are going to work. I can't find another number that can divide into that, so I'm going to call it prime. What about the number 24? Is that prime or composite? Well, there are plenty of numbers that can divide into this, so this is composite. I mean, for instance, 24, just as a single example, can be divided by 6, and that gives you 4. So that's not a prime number. What about the number 50? Can I divide something into 50? Well, of course I can. Other than itself and 1, I can. So I'm going to call it composite. 50 can be divided by 10, for instance, or 50 can be divided by 2. And the last one here, because we already have had some experience with this, is this prime or not? You start trying to divide by 3, divide by 7, you're going to find that you can't do it, so this is a prime number. Okay, so I just wanted to get a little bit of review on how to identify prime numbers or not, because ultimately when you write your factor tree, what you're doing when you get to the bottom is you're just checking to see if these are prime numbers. And if they are, then you can stop the factor tree. There's no reason to continue going any further. You've already drilled down to the most basic point. Okay, the next kind of problem that I want to do is I want to find all of the factors of the number that we write on the board. And we've actually done problems like this in the last section. We're just going to do a couple of them here just to refresh your memory on what we've done, because you're going to sort of compare and contrast to prime factorization. So here, we're not doing any prime factorization. We're just trying to see what the factors are. So we've already done these kinds of problems. For instance, let's say the number 8. How do you find the factors of the number 8? Well, basically, you try to list numbers that can divide into 8. The easy way to do that is just write down what you can multiply together to equal 8. 1 times 8 is 8. 2 times 4 is equal to 8. And I think that's about it. So as far as the whole number factors, regular old factoring, the factors are going to be 1, 2, 4, and 8. 1, 2, 4, and 8. And this is what we've done in the last section. Now notice these are not prime numbers. That's okay. A lot of times you're interested in just finding the regular factors of a number. Sometimes we're going to be interested in factoring into the prime factorization for other uses later on. All right, let's say 21. Well, how do we find the factors of that? We just try to multiply things together. 21 times 1 is 21, and 7 times 3 is 21, and those are about the only things that I can think of that can be multiplied together to give you 21. So the regular whole number factors is 1, 3, 7, 21. And those are what you would list for the regular factors. Notice that these are not prime numbers because we're not doing prime factorization here. We're doing a regular old factorization. All right. So final one, let's do just sort of since this is a review, we'll do the number 20. We can say 20 multiplied by 1 is 20. 2 times 10 is 20. And 4 times 5 is 20. And that's about all I can think of that can equal 20. So the actual factors here, 1, 2, 4, 5, 10, and 20. And again, notice these are not prime numbers because we're not doing prime factorization. Basically, when you do regular factorization, you're just listing every number that you can that will divide evenly into this number. The easiest way to do that is to try to write things that can multiply together. So 4 can be divided into 20. 5 can be divided into 20. 10 can be divided into 20. When we write the prime factorization, then basically we're only going to be interested in the factors that happen to be prime numbers. That's what's really what the difference is. So you're going to have a shorter list. All right. Next kind of problem that I'd like to do is I want to find the prime factors of a number. In other words, listing the prime factors. So the same thing that we just did a minute ago, listing the factors in a list with commas, but I only want to list the prime factors there. So the easiest way to do that is, for instance, here, let's do the number 8. So how do we proceed? When we're doing prime factorization, we do a factor tree. So you can pick anything you want. We can do 2 times 4. Now this 2 is already a prime number, so we don't continue down this leg of the tree, but this can be written as 2 times 2. Right? So what we've arrived at here at the bottom of the tree, these 3 numbers at the bottom, they're all prime, so we stop. We've already done the factor tree there, and we know that 2 times 2 times 2 is going to give us 8. So we've completed basically the factor tree. So if we want to list the factors of the number 8, the prime factors, it's just going to be the number 2 because that's the only thing that's at the bottom of this tree, and every number at the bottom of a factor tree by definition is going to be a prime number. Now you have a lot of duplication here. When you're listing the prime numbers as a list, you only need to list the number once because you're only listing numbers that are prime that can be divided in to 8. So the fact that it's listed here 3 times doesn't really matter when you're just making a list of prime numbers. Now later when we write the factorization out, then you'll need to include everything on the bottom of this tree. It just depends on what your problem really asks. And that's really what it boils down to. All right, what about the number 9? Well, prime factorization, we write it as 3 times 3, and we look here and we say, well, 3 is already prime. So the prime factors, PF, let's call it, the list, we're just looking in the bottom of the tree. The only number there is 3. We don't need to list it 2 times because we're just listing numbers that can divide into 9 that happen to be prime, and we already found what that is. You don't need to list any duplicates. Now, let's look at the number 15. The only thing I can think of would be 3 times 5. This is already prime, and this is already prime, so there's really nothing else to continue my factor tree. So the prime factors is, as a list, is going to be the number 3 and the number 5. Now, I just want to call your attention let's look at the first one we did, number 8. The answer we got, the prime factors, was 2. If we go down to our original problem, all of the factors of the number 8, all of the numbers that can divide into the number 8 are listed here, 1, 2, 4, and 8. When we get the prime factors, the only thing we're doing is looking in this list effectively and picking out the numbers that are prime. 1, by definition, is not prime. 4 is not prime. 8 is not prime. 2 is the only number that's prime, so that's the reason. In other words, this is an alternate way of doing it. I mean, all we're doing is finding the factors and then picking the ones that happen to be prime and putting them in a list. I'm doing it this way. I find it to be easier. Doing it this way is fine too, but I'll tell you one thing. This factor tree that we're doing is going to be very useful for you in algebra for other things, when you're dealing with square roots, for instance. So I want you to get comfortable with doing this because it's a very, very important thing. All right, let's go off to the number 18. What do you think about when you think of 18? Well, I think of 9 times 2. You might think of 6 times 3. That's fine. You'll get the same answer. 9 can be written as 3 times 3. So we're done with our factor tree because at the bottom, 3 is prime, 3 is prime, 2 is prime. So we stop. And the only numbers in our prime factorization that are prime is 2, 3. Is 2, 3. Prime factors of the number 18. We don't double list the number 3 because we're only interested in a list of numbers. We don't need to double up on those guys. We're just listing numbers that can divide into here that happen to be prime. Now, 9 is also a factor of 18. It's a regular old whole number factor of 18 because it can divide into 18. 6 is a whole number factor of 18, but we're not listing them here because we're only listing the prime factors, the factors that are prime numbers. That's really what this is, okay? All right, let's go and do the number 20. Well, I think of 4 times 5 when I think of the number 20. You might think of something else. The number 4 can be written as 2 times 2. This is prime, this is prime. 5 is also a prime number, so we're done. The prime factors is just going to be 2 and 5. And again, there's no reason to double list anything because we're just listing numbers that can divide in that happen to be prime. Let's go ahead and do a few more. How about 48? Well, there's lots of decisions there. You could do, lots of different numbers multiplied together. I happen to think of 8 times 6 is 48. Now, neither one of these are prime, so the 8 can be written as 2 times 4. 2 is prime, so I stop here, but 4 can be written as 2 times 2. 6 can be written as 2 times 3. So now we're done because we continue down and everything is a prime number. So at the bottom of the tree, okay, this is the bottom of the factor tree. All of these numbers here. Because this one is split into further numbers. So it's the bottom of the tree that we're interested in. And so if I'm listing the prime factors, right, it's only going to be 2 and 3. Because these are duplicated everywhere. So that's the answer, 2 and 3. So really, if you know how to multiply, you know how to do prime factors. What about 35? Well, I always think of 7 times 5 is 35, and it turns out that those are already prime numbers. This is prime and this is also prime. You can't subdivide them anymore. So when you're listing the prime factors, you just list 7, 5. Okay? Let's switch colors just for kicks. What about 36? I always think of 6 times 6 is 36. 6 can be divided as 2 times 3 over here and also 2 times 3. And we're done with our tree because this is all prime on the bottom of the factor tree. So if I were going to list the prime factors, they would be 2 and 3 because those are the factors at the bottom of the tree. There. And then finally, our last one for this kind of problem, let's do 80. There's lots of different ways you can do this. I always think of 10 times 8. 10 can be divided into 2 times 5. 8 can be divided into 2 times 4. This is prime, this is prime, this is prime, but 4 can be divided into 2 times 2. So I'm done at the bottom of the factor tree. These are the numbers that I care about. this one, this one, this one, this one, and this one at the bottom. So if I'm just writing a list of prime factors, I'm going to list the number 2 and the number 5 because these are all duplicated, 2, 5. So you should be pretty comfortable at this point with finding a list of prime factors. And basically it's the same sort of thing. The numbers that you list here can all be divided into 80, but they're the only factors that can go into that number that are also prime numbers. That's what we're doing. The easiest way to do it is to drill down to a factor tree down to the bottom of the tree, because at the bottom of the tree will be all the prime numbers that can divide into that guy. All right, now here in the last part, we're going to do something really similar. We're going to give a number, and we're going to, instead of listing the prime factors, we're going to write out what we call the prime factorization. It sounds complicated, but it's no different than what we've been doing. Let's tackle it by example. What we have here, let's say the number 8, right? We've done this one quite a bit, but you can milk a lot out of an example like this. So 8 is 2 times 4, and 4 is 2 times 2. So we're done. This is prime, prime, prime. We're done. Now, if we were just listing the prime numbers, the prime factors, we would just put the number 2 down. But when we list the factorization, prime factorization, the prime factorization, what you're doing is you're saying, all right, 8, the number 8 can be equal to 2 times 2 times 2. Basically, everything in the bottom of the tree multiplied together gives you 8. Think about it. 2 times 2 is 4. 4 times 2 is 8. So this is the answer. This is the prime factorization. But a lot of times you want to write it in terms of exponents, just to make it shorter and cleaner. So the way you would write it, if you were writing it in terms of exponent, would be 2 cubed. And that would be the answer. This is the prime factorization. This is still acceptable also, but if your problem tells you to write it in terms of exponents, that's going to be your answer. So I'm going to circle those as the answer. All right, what about the number 15? Well, we have 3 times 5. And those are already prime numbers. So if we were going to write down the factorization, we would say 15 is equal to 3 times 5. There's no way to write an exponent here. Nothing's repeated, so that's the prime factorization there. What about 18? 6 times 3 is 18. 6 can be written as 2 times 3, and 3 is already prime, so prime, prime, prime. So what we have here is the number 18 can be written as everything in the bottom of the tree multiplied together. 2 times 3 times 3. 2 times 3 times 3, the bottom of the tree. And think about it, 2 times 3 is 6, 6 times 3 is 18, so that does make sense. Now we do have a repeated guy here, so we can equally write this as 2 times 3 squared, because of that exponent. So you generally try to write it in terms of exponents if you can. It's the best way to go. All right, now let's say we have the number 20. Well, we can write that as 5 times 4. This is prime, but we can write this as 2 times 2. So we're done. Everything in the bottom of the tree is factored. Now, if we're going to write the factorization, that means you're actually showing the things that multiply together in the bottom of the tree, then you would say 5 times 2 times 2. Which can be written as 5 times 2 squared. 5 times 2 squared. All right, what about the number 90? There's a lot of different ways to go here. I like 10 times 9. And for 10, I like 2 times 5. And for 9, you can write it as 3 times 3. And everything in the bottom is now prime. Prime, 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 because you can't divide anything on the bottom by anything other than itself for 1. So if I'm going to write the prime factorization, I'm going to say that 90 is equal to everything multiplied here. 2 times 5 times 3 times 3, from these 3 here, which can be written as 2 times 5 times 3 squared. And that's the prime factorization of the number 90. All right, just a few more, just to get some practice. What about the number 28? A lot of different ways you can go here. 7 times 4 is 28. This is already prime. This can be written as 2 times 2. So everything's prime in the bottom. So if I were going to write the prime factorization, I would write it as the multiplication of these things. Or sometimes in your book, you'll read it as the product of these things. 7 times 2 times 2. 7 times 2 is 14. 14 times 2 is 28. But you can rewrite that as 7 times 2 squared. And if you can, you should try to write it with the exponent. That's just how most of the time you'll be expected. What about 40? Well, 10 times 4 is 40. 10 can be 2 times 5, and 4 can be 2 times 2. These are all prime numbers at the bottom. There's no way to go any further down there. So to write the prime factorization, you write it as, and I'm going to put the 5 first, since I know I'm going to have 2 times 2 times 2 here, 2 times 2 times 2 over here, which can be written as 5 times 2 to the third power, because I have 3 of them here. And if you think about it, 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, so that factorization does work out. The nice thing is you can always check it, because it's just multiplication. What about 63? This is the last problem. Well, 9 times 7 is 63. 7 is already a prime number, but 9 is not. You can rewrite that as 3 times 3. So everything in the bottom of the tree is prime. So in order to write this, you'll just multiply it together. 3 times 3 times 7. 3 times 3 is 9. 9 times 7 is 63. And you can rewrite this as 3 squared times 7 if you're going to keep it in terms of an exponent. So that's the prime factorization. So we've learned quite a bit in this section. It's a skill that you will use later on when you're dealing with more complicated algebra expressions. And the factor tree is going to come in handy when we start talking about square roots later on in algebra and simplifying all that stuff. So it's very, very important for you to know how to do these factor trees. Just keep one thing straight in your head. When you factor a number, in general, all you're doing, regular old factoring, is you're finding any number that you can to divide into that thing evenly. You know, like in this one, 63. 9 is a factor because it can be divided in there. But 9 is not prime, and that's why it's not listed in the prime factorization. Prime factorization literally means what it says. You're looking at the factors of the factorization only using prime numbers. Prime numbers are really special, and that's why we do this in math, because you'll see them pop up later on. It'll be useful for you to know how to do this. I'm Jason. I hope you've learned something in this section. Practice. Watch this video again if you need to. Work them out by hand. With practice and experience, you'll get good at it. And each little step on the journey here through pre-algebra is going to give you these skills so that when you get on into the more advanced topics, you have a great foundation and do well as you move on.